This video is super, super short because I'm only going to use this one example to make sure that you're all understanding this idea. We've talked about this before. We're going to keep talking about it, but it never fails. Sometimes we just can't wrap our heads around how two functions are different, but so similar at the same time. And what I want you all to remember that everything is based on domain. Okay. And you know what you can start doing, even you can start thinking continuity. Okay. So we're going to make a ton of notes all over this thing. And I want to make sure that you understand this. So what I've done is I've come up with two functions. They are very similar because they share all the same points, infinitely many points, except for the point at x equals 2. And I'm going to show you why. All right. This doesn't look like it should be a line, but it is with a hole in it. Okay. We'll talk about why that is. So let's come here real quick and we're just going to make a bunch of notes. So f of x equals a linear function x plus 2. Well, linear functions always have a domain of all real numbers, right? Really important. Okay, you can plug any number you want into x in a linear equation and you can get a y value out of it. As long as it's a linear function, okay? Now, if I put 0 in for x, I'm going to get a y-intercept of 2. Okay, so that's why we have x plus 2. And then this has a slope of 1, so I would have the point 1, 3. And then I could have the point 2, 4. Okay, so what that means is at 2, my function is 4. So I can actually say f of 2 equals 4. That's another really important piece of this, okay? I can say f of 1 equals 2, or sorry, f of 1 equals 3. I can say f of negative 1 is 1. I can say whatever I want, but I'm honing in on 2 for a very good reason, okay? So this function has a domain of all real numbers. I can plug 2 into the function and I get 4. And you know what? Since we've already talked about continuity, we can just go ahead and say, hey, this thing is continuous everywhere. So it is continuous on the real numbers. I don't ever have to leave the paper with my pencil to draw this line. All right, now we're going to come over to the other function, and I'm going to do a little bit of work up here actually. I'm going to go ahead and factor that numerator, and I notice that the numerator factors into x minus 2 times x plus 2. And then I want to remind you of a previous lecture that I did, or a previous video that I did, where I said, well, we can't cancel these x minus 2s unless we say specifically that x cannot be 2. And why? Because if x is 2, then my denominator is 0 and I have a problem. So what this is saying is this function is x plus 2 for all values except 2. So they're not the same function entirely. They have different domains. So I'm going to go ahead and rewrite the domain of this function down here. So I have negative infinity to 2, and then I could be anywhere from 2 to infinity. So negative infinity to 2, I can select any number in here and it will work, or I can select any number in this interval and it will work. So as soon as you see that the domains are different, the functions are different. They're not the same. All right, let's go ahead and see here. F of 2. Well, we should know that this is undefined. If we plug in 2 here, we get 2 squared minus 4 divided by 2 minus 2. So we get 4 minus 4 over 2 minus 2. And that's 0 over 0. Now in limits, that's called your indeterminate form, meaning we can't determine the value of the limit, so we do more work. And this is where we bring in the factor cancel and the algebra that we would use there. And I'll go into limits in just a second with this, but in algebra, as soon as I see that I'm dividing by 0, all I can say is that this thing is undefined at 2. Which makes sense because we already said that the function doesn't exist at 2. So 0 over 0, when you see something like that, you should automatically say to yourself, graphically, I have a hole. I have a hole in the graph of my function. This is also known as, x equals 2 is known as a removable discontinuity. And it's a removable discontinuity because I can keep the shape of my line going, and I just come in with a cookie cutter and I pluck out the point at x equals 2. So I'm removing the point at x equals 2. So I can't plot an f of 2. That's not possible here, like I could do here. Okay. So I have, graphically, I have a hole at 2. In terms of the existence of the function at 2, it's undefined at 2. I just realized I wrote f here, and it should be g, excuse me. The function does not exist at 2. It's undefined at 2. And then lastly, another thing that you could say is the function is discontinuous at 2, and you can give it sort of an explanation there, and you can say it's a removable discontinuity at 2. That relates you to the graphical interpretation of a hole. All right, now, last thing I want to do real quick is say that the limit as I approach 2 on x plus 2 is the same, 4, as the limit as I approach 2 on this function g, that limit will be 4. I cannot call this f of 2. I'm going to call it L for limit, because remember, limit means I need to get close, but I don't actually need to get to that value. So as I approach 2 on the x-axis for both of these functions, I'm riding the line toward this point 2, 4, this hole at 2. And this point is at the y value of 4, and this hole is at the y value of 4. So while the function exists, while f exists at 2, but g does not, both f and g's limits exist as x approaches 2. So I can say the limit as x approaches 2 of f of x is the limit as x approaches 2 of g of x, and in both cases that's going to be 4, but f and g are not the same function. So you'll hear me say quite often, limit existence does not indicate function existence, because I don't have to get to this hole. I just have to get arbitrarily close to it. All right. And so while, yes, the two limits are the same, the functions are not at 2. Okay.